Today I was in a museum for the first time in a long time, and when I noticed that an artist often used the golden ratio in his paintings, I remembered my school days. I remembered a question that I asked myself, and I'm only now trying to answer with my knowledge of mathematics and physics. But first I will introduce the golden ratio. The golden ratio is a ratio in a picture which should build up tension. For example, in Michelangelo's painting, the fingers of God meet exactly in this ratio, where there is a tension between the dominant side and the smaller side. Mathematically, the golden ratio has the property that the ratio between the larger side to the total length of the picture is the same ratio as the smaller side to the bigger side. This means if we bring the strips closer to our eyes, the strips will eventually look the same. When I painted a picture of a ship, I tried to hit the golden ratio from the feeling. Exactly in this, I wanted to set the mast of my sail. Afterwards, I checked how exactly I hit the golden ratio. Well, just off the mark. My question was now if my mast was still in the golden ratio, or was it too far away? Maybe my ratio was just a bit less golden. Maybe it was a silver ratio. I was wondering if we could assign a golden value to each ratio of the picture. And the golden ratio would be the one where the golden value is the greatest. Is it possible to draw a curve that assigns a golden value to each ratio of an image? The golden curve maps the ratio to the perceived tension. Does a golden curve exist, and if so, how can it be calculated? That the left and the right golden ratios of a picture are the maxima is certain, but what are its minima? For symmetry reasons, one could come to the conclusion that the center is a minimum. But there is also another argument. We take the picture of Michelangelo. If both fingers would meet in the middle, both sides would be completely balanced and there would be no tension. The golden ratio is often used for the position of people in camera shots. The position in the middle would have an opposite effect. For constructing a golden curve, we could now simply put a normal distribution about both golden ratios and we would be done. We could now just vary the variance and have a simple answer to our question and the first golden curve constructed. The problem of this approach is that a deviation to the left or the right of the golden ratio does not matter, and no deeper understanding of the golden ratio and the golden curve arises. While searching for something deeper than the normal distribution solution, I looked through the Wikipedia article of the golden ratio. It says that the golden ratio is the ratio which can be the worst approximated by rational numbers. For example, pi can be approximated well by 3 or 22/7. The golden ratio can be approximated much worse by rational numbers like 22/7. My teacher said in my school time to me, the golden ratio is about 2/3 of a picture. I would like to discuss this statement in this video. The golden ratio has the property of being particularly badly approximable with rational numbers like 1/3 or 2/3. If this is the fundamental property of the golden ratio, then it is exactly the opposite of 2/3. The fact that the golden curve should have a minimum at the rational number of 1/2 and a maximum at the golden ratio, which can be only very poorly approximated by rational numbers, reminded me to something completely different from arts, namely music. In music, frequency ratios like 1/2 or an octave should sound consonant or good to our ears. Frequency ratios, which are only badly approximable by rational numbers, should sound dissonant, like 1 divided by square root of 2. Also, a frequency ratio of 3/4 sound consonant. Following, we are actually looking for a curve that represents the approximability of a ratio with rational numbers. The golden ratio is now neither a half, not a third or a fourth. and is not well described by rational numbers. Is it exactly this property that the eye does not recognize a pattern of 1/3 that makes the golden ratio so exciting? I drew a line on a piece of paper. In the city, I asked people if they could tell me if the line was at 1/2, 2/3, 1/5 or so on the paper. Most of the people could tell the ratio up to 3/4, but it was more difficult for 2/5 or 2/7. With the ear it's different. Musicians could easily recognize patterns of 2/7 or 3/5. In music as well as in art, the eye or ear must approximate ratios. Since the eye is worse at resolve ratios, it may be not the same golden curve that we are looking for, but the concept of approximability is the same. How to build a curve for the approximability of numbers by rational numbers? Any number can be approximated by a fraction of arbitrary large denominator and nominator, but such a fraction would be certainly not recognized by the eye. We want to do again the normal distribution approach, but this time we want to put the normal distributions around the rational numbers, like 1/2, 2/3 or 1/3. Since the half is much easier to recognize by the eye, we choose the normal distribution here to be higher. Afterwards, we turn the curve over and get a curve that is similar to our old approach. But this time the golden curve is justified by the bad approximability of the golden ratio by rational numbers. In music, the golden ratio sounds dissonant, but also other ratios sound dissonant. If one would compare both disciplines, arts and music, in which both the approximability of rational numbers plays an important role, we could ask ourselves whether the golden curve could have more maxima than just the golden ratio. I wonder if there are more ratios out there which have similar properties to the golden ratio. Further back in the Wikipedia article, a plant was shown which always arranges its leaves around the same angle and uses the golden ratio. This gave me an idea that might help us to construct a good golden curve. For this, we must first understand what a geometric spiral is. The principle is as follows. We go in a circle a fixed angle alpha further and set after 1 centimeter a point. Then we go again the same angle further and set after 2 centimeter a point. We go again alpha further and set 3 centimeter from the origin a point, and so on. This results in such a spiral. For alpha 3.883 radian, and in this spiral for alpha equal 1.646 radian. Now we want to see how such spirals look like for different alpha. For this we use the conversion of alpha to x is equal to alpha divided by 2 pi. If x is equal to 1, it goes around once. If x is equal to 0.5, it goes always a half time around the circle to the next point. The result is as follows. We see that for x about 1/3, the spiral arms form an ordinary pattern. Now we let the video run on. At the golden ratios, so x is equal to 0.618, the points distribute themselves equally about the surface. This property is also used by the plant of the Wikipedia article. We see that rational numbers form ordinary patterns, while irrational numbers distribute the points more equal about the whole surface. I was wondering if there is any way to use this to construct a golden curve. We see that for x is equal to the golden ratio, the points are maximally well distributed over the surface. And for our proposed minimum of the golden curve, the points are distributed along one line. I was looking for a value that tells me how messy or ordered the points are distributed for each spiral pattern. We are looking for a function that maps a ratio with the help of the spiral to the golden value. I tried a lot of things and came up with a solution that sounds far-fetched at first but works very well in the end. The idea is as follows. We construct partial geometric spirals for each geometric spiral. The first partial spiral goes through each point, the first, the second, the third, and so on. The second partial spiral goes through every second point, the second, the fourth, the sixth, and the third goes to every third point, the third, the sixth, the ninth, and so on. Now we look at the point densities on the spirals. Shown are the first 10 points along the path on the geometric spiral. On the second spiral, the points are not very dense. On the fourth, they are the densest, and on the eighth, they are the second densest. This is because the ratio of 0.262 can be well approximated by 1/4 or 2/8, but not by 1/2. The number that is shown is the point density of the first 10 points per distance on the geometric spiral. Let's look at the same for the golden ratio. We see that all partial spirals are less dense than in the previous example. Further, we see with the point densities that the golden ratio can be best approximated by 2/3 or 5/8. My approach is that we should add up all the point densities on the golden ratios to get a golden value. My idea to calculate a golden curve is to construct a geometric spiral for each ratio. Then we construct the partial geometric spirals up to a given order. Then we calculate the point densities on the geometric spirals and sum them up. At the end we get a value for each ratio. If we now sum up the point densities on these spirals up to degree 20, we get this curve, which has maxima for ordered diagrams and minima for disordered ones. If we take the reciprocal of the curve, we get the golden curve. We see that something close to the golden ratio is the maximum of the curve. Let's make sure that the curve represents well the order and disorder of the spirals. Now this curve has far too many maxima and minima that our eye can't resolve. It describes well the disorder and order of spirals of about 100 points. But what is if we zoom closer to the center of the spiral? Then we can't resolve so many maxima and minima. My solution to the question of whether my golden ratio of the sailboat is less golden looks like this. The more golden color, the more golden is the ratio. But if the eye now also resolve ratios like 1/3 and not only 1/2, the result looks like this. If 1/4 is also resolved, the golden curve looks like this. If up to 1/4 is resolved, the partial spirals must be summed up to the fourth partial spiral. If up to 1/5 is resolved, then up to the fifth partial spiral. There is always another golden number between the blue, not golden places, so the rational numbers, which belongs to the family of the golden ratio. We can now put the color diagram under the picture and make a composition analysis of it. We can now decide for each image specifically if the ratio of 1/3 is also resolved or even a ratio with a 5 in the denominator. It's up to the viewer if he feels the 2/3 or 1/3 of a picture still as untensionless and symmetric.